Picture a black hole doing something it isn't supposed to be able to do. It's feeding. Not at a normal rate, 40 times faster than physics says it should be able to handle. Push a black hole past a certain point, and the radiation pouring off its own meal is supposed to shove the food away, choke the whole system, shut it down. That's the rule. It's not really up for debate. This thing broke the rule anyway, and it kept feeding. For years, nobody could even find it. It was blazing in X-ray light and completely silent in every other wavelength. A ghost, hiding in plain sight from two of the most powerful telescopes humans have ever built. Then the James Webb Space Telescope turned toward it. What came back didn't just explain one impossible object. It cracked open a new picture of what black holes are actually doing to the galaxies they live inside, starving them, tearing pieces off their neighbors, hiding behind walls built out of their own light, even reaching down to destroy individual molecules one at a time. This is what James Webb actually found happening inside and around black holes. Real data, published over the past few years. And by the end of this, you'll understand why astronomers are calling it a full rewrite of the rulebook. For decades, our best eyes on the universe had a serious blind spot. Hubble and the Chandra X-ray Observatory gave us extraordinary images, but they could only catch the most extreme light out there, blazing X-rays, ultraviolet flares screaming off the inner edge of a black hole's accretion disk. Anything colder, denser, or wrapped in dust just disappeared from view. And it turns out that unseen material, the cold stuff, the dusty stuff, is exactly what decides how black holes and their host galaxies grow up together. James Webb was built to see straight through that dust. Its instruments, NIRS and MIRI, work in infrared light, basically night vision for the cosmos. Except instead of picking out body heat in a dark room, it's picking out the coldest, most invisible gas surrounding some of the most violent objects that exist. That's the tool that finally caught our ghost. Its name is LID-568, and it was buried inside the Cosmos survey data, from a time when the universe was only about 1.5 billion years old. Chandra had actually caught it years earlier, sitting inside 4.6 million seconds of X-ray exposure, one of the longest stares in the entire survey. Something was clearly there, blazing in X-rays, but invisible or near infrared light, nothing. No glow, no obvious position to point a telescope at. Astronomers call this a near-infrared drop-down, loud in one wavelength, invisible in every other one. That's a real problem, because JWST's main spectrograph usually works like a straw. You point it at one precise spot, and it tells you exactly what's there. But you can't aim a straw if you don't know where to point it. So a team led by astronomer Hwan Su at the Gemini Observatory used a different tool, an integral field spectrograph. Instead of one straw, imagine a camera where every single pixel captures its own complete spectrum of light. Wherever this thing was hiding in the frame, they were going to catch it. In November 2024, they did. LID-568 turned out to be fairly unremarkable in one sense, about 7.2 million solar masses, roughly the same weight class as Sagittarius A, the black hole sitting at the center of our own galaxy. Nothing unusual there. What was unusual was how fast it was eating. 40 times the Eddington limit. Here's why that number matters. The Eddington limit is the universe's built-in speed limit for feeding a black hole, named after the British astrophysicist Arthur Eddington. It marks the exact point where radiation blasting off superheated infalling gas gets strong enough to cancel out the black hole's own gravity. Cross that line, and the radiation is supposed to win, blow the surrounding gas away and starve the black hole out. It isn't a suggestion. It's supposed to be physics. LID-568 blew past that line by 40 times and didn't stop. So how does something like that survive its own dinner? The answer was tucked into the spectrum. Massive outflows. Gas getting blasted outward at 500 to 600 kilometers a second, somewhere around 300 to 370 miles, every single second. This wasn't the black hole failing, it was venting. By hurling a chunk of its own meal back out into space, it released just enough pressure to keep the rest of the feed stable, the same way a pressure cooker hisses out steam so it doesn't blow the lid off. This one object might solve something much bigger. How do black holes get so enormous so early when the universe had barely had time to get going? Maybe they don't need a head start. Maybe a small seed, just 100 or so solar masses, can go through short, violent feeding binges like this one. Gorge far past the limit, vent the pressure, rest for a few million years while the gas cools and drifts back in, then feast again. Do that enough times, and a modest seed can turn into a monster well within the timeline the early universe actually gives you. Feeding is only half of it though. Some black holes turn into killers. Almost 12 billion light years away sits a colossal galaxy that researchers nicknamed Pablo's Galaxy, after one of the astronomers who first proposed studying it. Officially, it's called GS-10578. It's a giant, something like 200 billion solar masses, and at its age it should still be a stellar nursery, cranking out new stars. Instead, it's dead. Star formation shut off somewhere between 11.5 and 12.5 billion years ago. Astronomers call this quenching. The galaxy went from young and blue to old and red, and it isn't coming back. The leading theory has always been that a galaxy's own black hole can do this, blasting out winds strong enough to strip away the gas needed to build new stars. The problem was, the math never worked. Older telescopes could only detect thin, blazing hot winds glowing in X-ray and ultraviolet light, and there simply wasn't enough mass in those winds to kill star formation across a galaxy this size. Webb found a piece that had been missing the whole time. Buried in the data was a stream of gas that gave off no light of its own at all, cold, dense, and completely dark. The only reason anyone could see it was that it blocked the light of a different galaxy sitting behind it, like a shadow falling across a wall. That invisible wind is moving at 2.2 million miles an hour. For scale, that's roughly 1,500 times the top speed of an F-16 fighter jet. That's the missing mass. This cold, dark wind alone carries away far more gas than the galaxy needs to keep forming stars. The black hole isn't just influencing this galaxy anymore. It's suffocating it. And here's the part that should have broken the whole theory. Every simulation predicted that a kill this violent would tear a galaxy's structure apart, turn a clean, orderly disk into a chaotic, shapeless blob. But when researchers actually measured how the stars in Pablo's galaxy are moving, they found something almost eerie: a calm, orderly, rotating disk, completely intact. The black hole took away this galaxy's future without touching its shape. Less like a bomb going off, more like one precise cut from a surgeon. A black hole can feed at impossible speeds. It can slowly strangle its own galaxy. Some of them go even further. They eat their neighbors. Reach back further still, to what astronomers call a redshift of about 6.2. Their way of measuring how far back in cosmic time you're looking. This is among the earliest galaxies ever studied in this kind of detail. There's a quasar here called PJ308-21, powered by a black hole weighing 2.7 billion solar masses, feeding at close to its absolute maximal rate. Earlier observations with the ALMA array had already picked up something strange nearby, companion galaxies sitting close enough to be interacting. Webb mapped the entire system in one pass, tracing multiple wavelengths of light with incredible precision. What came back looked almost like a crime scene photo. On one side sat a companion galaxy that's remarkably pristine, low in heavy elements, barely touched, still forming stars the old-fashioned way. On the other side, the quasar's home galaxy, choked in dust, saturated with heavy metals, lit up with every signature of an active black hole tearing through everything around it. And connecting the two, Webb found something remarkable: a visible bridge of gas, physically stretching between the pristine companion and the quasar's home, carrying clear signs that material was crossing directly from one to the other. This isn't a model. It isn't a guess. This is a galaxy already more than 100 billion solar masses, caught in the act of ripping apart a neighbor and pulling the pieces into itself. Not every early black hole is a monster, though. Some of them start out surprisingly small. In July 2023, astronomer Rebecca Larson and her team, working with data from the CER survey, found a black hole inside a galaxy called CER's 1019, from just 570 million years after the Big Bang. At the time, it was the most distant active black hole ever confirmed. But here's the twist. Unlike the billion solar mass giants popping up at similar distances, this one weighed in at only about 9 million solar masses, barely bigger than the black hole sitting at the center of our own galaxy today. Its host galaxy doesn't look like one clean structure either. Instead of a single smooth disk, Webb resolved it into three separate glowing clumps, all forming stars violently while the black hole feeds in the middle of the mess. It looks less like a finished galaxy and more like a construction site that hasn't decided what it's building yet. The Sears team went on to find more of these lightweight black holes at similar distances, each weighing around 10 million solar masses. Together, they sketch out a whole population of small, unglamorous seeds scattered through the early universe, overlooked building blocks that would eventually grow into monsters like PJ 308-21. As Webb kept staring deeper into the universe, it kept turning up small, oddly red, compact objects nobody had really documented before. Astronomers started calling them little red dots. A few of them came with a genuine puzzle attached. In certain early quasars, including a well-studied one called UALAS J1120 plus 0641, the light didn't match the standard formula. High-energy elements that should have been glowing brightly this close to a black hole were strangely faint, muted by a factor of 3 to 4 times what the models expected. Researchers, including Sarah Bosman, eventually landed on an explanation, and it comes down to shape. Around a black hole feeding this hard, the inner accretion disk isn't thin and flat the way it's usually drawn. Radiation pressure puffs it up into something thick, almost like a donut with a wall instead of a hole. That thick inner wall physically blocks the harshest X-rays and ultraviolet light before it ever reaches the gas further out. The high-energy chemistry gets stunted, while the gentler light slips right past. Some of these black holes aren't weak at all. They're just hiding behind a wall built out of their own radiation. Here's where this gets almost absurdly specific, all the way down to individual molecules. Scattered through galaxies is a family of carbon-based molecules called PHAs, essentially interstellar soot. Astronomers have used them for years as a kind of measuring stick for star formation, since young, hot stars light them up in a very specific, predictable way. But when Webb's MIRI instrument looked closely at galaxies with active black holes, it found something nobody expected. The radiation doesn't treat all of that soot equally. It selectively destroys the charged, ionized version of these molecules while leaving their neutral, uncharged cousins almost completely untouched right next door. Researchers studying an emerging galaxy called NGC 6240 found it goes even deeper. One particular chemical signature actually splits into two nearly identical wavelengths, one from long carbon chains, one from short ones. Close to the black hole, the long chains get stripped away entirely by high-energy ultraviolet light. Only the short, tightly bound chains survive. It's almost like a razor, the radiation shaving the dust grains clean, molecule by molecule. That's not just a strange detail. It means every measurement of star formation near an active black hole, using this decades-old method, has probably been a little off. Not because the stars aren't there, because the black hole has been erasing the evidence all along. And you will now be afraid? Which brings us back to the biggest question of all. Where do these things even come from? For years, astronomers have argued over two competing origin stories. Either a black hole starts as a light seed, the collapsed core of a massive dead star, maybe 100 solar masses to begin with, or it starts as a heavy seed, born when a giant cloud of primordial gas collapses directly into a black hole, skipping the star phase completely, starting out somewhere between 10,000 and 100,000 solar masses. A galaxy called UHZ-1 may have finally settled the argument. Researchers Akos Bogdan and Priyamvada Natarajan combined data from Webb and Chandra and found something genuinely bizarre. In a typical galaxy today, the central black hole makes up only about 0.1% of the galaxy's total stellar mass. In UHZ-1, the black hole's mass is almost equal to the mass of every star in its entire host galaxy, combined. There's no version of a normal dead star growing that fast, that early, relative to everything around it. The only explanation that fits is that this black hole skipped the star phase entirely and was born enormous, straight out of a collapsing cloud of gas. It's direct, physical evidence that at least some of the universe's earliest black holes never had to wait around to grow up. So, what did James Webb actually find inside the environments of black holes? It found one gorging at 40 times the speed physics allows, venting its own violence just to keep from tearing itself apart. It found a galaxy being quietly suffocated by a wind you'd never see with your own eyes, its shape somehow left untouched. It found a black hole caught mid-bite, physically pulling a neighboring galaxy apart. It found tiny chaotic seeds barely bigger than our own galaxy's black hole, hiding since the earliest chapters of the universe. It found black holes wearing shields built from their own light, and radiation precise enough to erase individual molecules one at a time. None of that fits the old picture of a black hole as some quiet drain at the center of a galaxy, just sitting there, gathering mass while everything else happens around it. These are active, violent, sculpting forces, feeding, starving, merging, seeding, shaping the galaxies they call home, from the universe's first billion years all the way to now. And this is likely just the start. WED is still out there, still finding objects that shouldn't exist by the rules we had 5 years ago. Every one of these discoveries raises the same quiet question. What else is still hiding out there, waiting for the right telescope to finally notice it? If stories like this, the universe quietly rewriting its own rulebook, are the reason you're here, this is exactly what we do at Cosmos Coastline. Subscribe and come find the next one with us.